In the last few lectures, we had derived the conservation equations for mass, momentum and energy. Okay. So, mass conservation partial C by partial T plus divergence of V times C is equal to d del square C, which is basically minus of the divergence of the flux. Okay. Mass conservation equation, assumption made here is that diffusion coefficient is a constant. Okay. The assumption made here is that the diffusion coefficient is a constant. Okay. Momentum, so in general, of course, I can have a source of mass. So, I should just add that source here, which is minus divergence of the flux plus the source. Here fixed law of diffusion, J is equal to, and we have assumed that the diffusion. Similarly, for the temperature field, partial T by partial T plus divergence of V times the temperature is equal to alpha del square T plus any energy source by rho Cp. Okay. Written as minus the divergence of heat flux plus okay, where alpha is equal to the thermal conductivity by rho Cp, okay, and Q is equal to minus K grad T. As temperature is proportional to the gradient of the heat flux goes from higher temperature to lower temperature. Similarly, the mass flux is equal to minus d times grad C. And finally, Navier-Stokes mass and momentum conservation equations for a Newtonian fluid incompressible. Okay. Divergence of velocity is equal to 0. Okay. And rho into partial V by partial T plus V dot grad V. Plus a body force density, okay, where mu is the viscosity coefficient, P is the pressure. Okay. And note here that there is a dot product between the velocity and the gradient in this expression, okay, for an incompressible fluid. And for potential flow, inviscid, that is viscosity is equal to 0, irrotational, del cross V equal to 0, curl of the velocity is equal to 0 or the vorticity equal to 0. Okay. You can write the velocity as the gradient of a potential. This is a significant simplification because the velocity is a vector, it has 3 components. When it is irrotational, you can write it in terms of just a scalar function, the potential, okay, the velocity potential. Okay. So, it is a significant simplification in this case. You go from 3 velocity equations, that is this equation actually contains is a vector equation. That means that it contains equations for the x, y and z components of the velocity individually. Okay. So, divergence of velocity is a scalar equation, divergence of a vector is a scalar. So, divergence of velocity equal to 0 is a scalar equation. Momentum equation is a vector equation. It has 3 components, the x component, y component and z component. When we write the velocity as the gradient of a potential, then we are greatly simplifying it because we are reducing it from a vector to the gradient of a scalar, a single function. Okay. Once you do that, automatically the Laplacian of the potential has to be equal to 0. That is divergence of velocity, divergence of gradient of potential. So, Laplacian of potential has to be equal to 0. Momentum equation I showed you last time reduces to rho partial phi by partial t plus half rho v square plus p plus any potential energy is equal to a constant. This is the Bernoulli equation. okay, where half rho v square basically is v dot v. Okay. So, this can be considered as the kinetic energy. Okay. Half rho v square is the kinetic energy per unit volume. This is the potential energy per unit volume. For example, if you had a tank at a height z, this would be minus g times z. Okay. So, the potential energy per unit volume, I am sorry, g times z. So, this is the potential energy per unit volume, p is the pressure, and this basically represents the acceleration term in the Bernoulli equation. So, that is what we had completed in the last lecture. Okay. Now, I will go on to unidirectional transport. Where there is variation only in one particular direction and in time. Okay. There is variation only in one direction and in time. That direction I will consider as the z coordinate. Okay. Okay. So, this is the z direction. There is a variation only in this direction and in time. Okay. So, let us take the simplest case for steady transport. Okay. For steady transport, okay, if I took a steady transport, you know that the equation, for example, for the temperature field is partial T by partial T plus del dot V t is equal to alpha del square T. Steady transport, the time derivative is 0, and steady transport, if we consider 0 velocity, right, then we just get alpha del square T equal to 0. And if it is unidirectional, okay, you get partial square T by partial z square is equal to 0, okay, which implies that T is a linear of z. Okay. Distance z between these two. Okay. So, for steady transport in the Cartesian coordinate system, the slope of the temperature has to be a constant, second derivative has to be 0. Basically, it says that the heat flux is equal to 0. Okay. So, that is what is meant. Okay. Of course, if you have a source in the field, you have to solve the equation d square T by dz square plus s is equal to 0, and once again you integrate 2 times with respect to z in order to find out what is the temperature field subject to boundary conditions. Okay. Here we will start examining unsteady transport. Okay. We will start examining unsteady transport, where there is both a time dependence and there is a spatial dependence in one direction. Okay. Where there is both time dependence and there is spatial dependence in one direction. Okay. Let us take the simplest case. Okay. We have a region z greater than 0 bounded by a surface at z is equal to 0. Okay. Initially, the temperature is T naught, T infinity everywhere. Everywhere. Okay. Initially, the temperature is T infinity everywhere. Okay. And at time t equal to 0, we set the temperature of this bottom surface, okay, equal to T naught. Okay. Okay. Which implies that at t equal to 0, T is equal to T naught at z is equal to 0. Okay. And then we want to know how the temperature in this fluid evolves with time. Okay. Since there is no flow, or even if there is flow in the x direction, okay, in the along the plate, okay, it does not matter. Okay. There is no variation in temperature in the x direction. So, there is no heat transfer in that direction. Okay. We assume that it is an infinite system along the plane of the flat plate, which is whose temperature is being increased. There is no variation in the x direction. Okay. And therefore, the temperature equation becomes partial T by partial T is equal to alpha partial square T by partial Z square. Okay. So, T is equal to T naught at the surface. Initially throughout the fluid T is equal to T infinity. Okay. So, the first thing we can do is we can define a scale temperature. Okay. T star is equal to T naught minus T. If I define it this way, you see that this corresponds to T star equal to 0 in the fluid. Okay. T star will be equal to 1. Okay. At the surface T star is equal to 1. Okay. And if I substitute this, I substitute for the temperature here into the into the energy conservation equation. Okay. You can easily see that the T naught minus T infinity will cancel out on both sides, and the equation for the temperature just becomes partial T star by partial T is equal to alpha by partial Z square. Okay. So, that is the energy conservation equation for this case. Okay. And the boundary conditions are that far from the surface, T star has to be equal to 0. Okay. So, therefore, T star is equal to 0 for Z going to infinity, far from the surface, okay, because that is the condition that you are applying, far from the surface. At the surface T star is equal to 1, okay. At the surface the temperature is equal to 1 at Z is equal to 0. Therefore, the boundary conditions at the two boundaries, at the bottom surface which is heated, T star is equal to 1 at Z is equal to 0, far from the surface the temperature is equal to T infinity, and then there is an initial condition. Okay, that T star is equal to 0, right, at initial time, just when the heater has been switched on, throughout the medium T star has to be equal to 0. Okay. Only at the surface itself T star is equal to 1. Therefore, T star is equal to 0 at T is equal to 0 for Z greater than 0. Okay. So, those are the boundary and initial conditions, okay, for this particular configuration. Heat conduction into an infinite medium, okay, heat conduction into an infinite medium. Okay. So, how do we solve this? So, as you noted, we had defined this as the scale temperature T star. Okay, we had defined this as the scale temperature T star. How do we scale the length? Okay, the distance coordinate Z. Okay. You can see that this is conduction into an infinite medium. So, there is no length scale in this problem. Okay, so, there is no length scale in this problem because this conduction into an infinite medium. There are only 3 coordinates and parameters here. Okay, there are only 3 coordinates and parameters here. The 2 coordinates are the time coordinate and the Z coordinate. Okay, Z coordinate and time, those are the coordinates, and there is only one parameter alpha. Okay, there is only one parameter alpha. From this 3 parameters, they contain 2 dimensions, length and time. From this you can create only one dimensionless group. Okay. From this you can create only one dimensionless group. Okay. And that dimensionless group that you can create is what is called psi is equal to Z by root alpha t. Okay. Note that this parameter alpha has dimensions length square t inverse. It is a diffusion coefficient, a thermal diffusion coefficient, length square t inverse. So, alpha times t has dimensions of length. Okay. Therefore, Z by root alpha t is dimensionless. Okay. This is what is called a similarity variable. This is what is called a similarity variable. Okay. because there is a deficit of dimensions, there is no length scale in the problem, there is no time scale in the problem. Time goes from 0 to infinity, z goes from 0 to infinity. Based upon dimensional analysis, we can get only one dimensionless group containing both the z coordinate and time. That means there has to be some similarity in the way the temperature varies with z and time if these are related in this manner. Okay. So, it is called a similarity variable. Okay. So, if we can express the temperature field in terms of this similarity variable alone, note that the original temperature field was dependent both on T and Z. Okay. The original temperature field, that equation for the temperature, depended on T and Z. If I can reduce Z and T to just one variable, okay, then I should be able to express the entire equation in terms of that variable and also express the boundary conditions in terms of that variable. If I can do that, the entire problem, the temperature field, can be expressed in terms of only that similarity variable. So, let us see how to convert the equation. The original temperature equation that depends on independent variables T and Z into an equation that depends only upon this similarity variable psi. Okay. So, you do that by differentiation by chain rule. Okay. Partial T by partial Z is equal to partial T by partial psi times if I have expressed it in terms of only one variable, then it just becomes dt, the total derivative, by d psi. If temperature field depends only upon psi, times partial psi by partial z is equal to dt by d psi times 1 by root alpha t. Okay. That is the first derivative. Second derivative, okay, is going to be equal to d by d psi of this whole thing right times partial psi by partial z, which is equal to 1 by alpha t d square t by d psi square. Okay. And then the time derivative, partial t by partial t. I should note here that I should write all of these in terms of the scale temperature, okay, because I have already transformed to the scale temperature. Okay, is equal to dt by d psi into partial psi by partial t. Okay. Okay. Differentiate by chain rule. Okay. So, dt by d psi into z by root alpha into the derivative of 1 over root t is minus 1 by 2 t power 3 by 2. Okay. I have a square root of t in the denominator here. Derivative of 1 over root t is minus half into t power minus 3 by 2. Okay. Rewrite this as separating out the t by t power 3 by 2 by as t times square root of t. Okay. So, this will be equal to dt by d psi into minus psi by 2t. Okay. So, that is what you get by differentiation by chain rule, okay, for all the terms. Okay. So, the original equation was partial t is equal to alpha d square t by dz square. Okay. And if I substitute these two, this one for the right hand side, this one for the left hand side, okay, then I will get minus psi by 2 t dt star by d psi, okay, is equal to alpha by alpha t d square t star by d psi square. And you can see that the alpha will cancel, the t will cancel, okay, and I get an equation that depends only upon the similarity variable psi. Okay, I get an equation that depends only upon the similarity variable psi, okay, and that equation is of the form minus psi by 2 dt by d psi is equal to d square t by d psi square. Okay, so, that is the equation for the scale temperature in terms of the similarity variable. So, I have transformed the equation for the scale temperature. I also need to transform the boundary conditions. What were the boundary conditions? Okay. At the surface, okay, at z star is equal to 0, I had t star is equal to 1. Z star is equal to 0 corresponds to, okay, psi is equal to 0, because psi is equal to z by root alpha t. Okay. So, at psi is equal to 0, the temperature is equal to 1. Okay. Then as z star goes to infinity, t star is equal to 0. Okay. Z star going to infinity is equivalent to psi going to infinity, because psi is z by root alpha t. Okay. So, this corresponds to psi going to infinity. Okay. Those are the two boundary conditions. Initial condition at t equal to 0. So, these are, I am sorry, it is not z star, this is just z, okay, and z greater than 0, we get t star is equal to 0. That is the initial condition. Above the plate, anywhere above the plate at t equal to 0, when the heating has just been switched on, temperature has to be equal to 0 above the plate. Okay. Z greater than 0 and t equal to 0. Note that psi is equal to z by root alpha t. So, z greater than 0 and t equal to 0 basically corresponds to psi going to infinity. Okay. So, these are the equations for the boundary conditions, and you can see that when expressed in terms of the similarity variable, these two boundary conditions, when expressed in the terms of the similarity variable, these two boundary conditions reduce to the same condition. Okay, when expressed in terms of the similarity variable, these two boundary conditions reduce to the same equation, same condition in terms of psi. Psi goes to infinity, t star is equal to 0. And it is necessary for them to reduce, because the original equation had first derivative with respect to time, second derivative with respect to z. You needed two boundary conditions, one initial condition. Transformed equation in terms of the similarity variable here, okay, contains only a second order equation for psi, and therefore, you can have only two boundary conditions in the psi coordinate, the similarity variable. Okay. So, therefore, I need to solve this equation. Okay. So, I need to solve this equation subject to these boundary conditions for the psi coordinate. Okay. So, how do I solve that? Okay. So, the simplest way to do that is to write the derivative as a new variable t star prime. Okay. Okay. I write this as a new variable t star prime. Then my equation, this equation now becomes minus psi by 2 t star prime is equal to d T star prime by T psi. Okay, that is the equation that I get. Okay. I can cross multiply to get by D by T star prime. Okay. Integrate once to get log of T star prime is equal to minus psi square by 4 plus some constant a. Okay. And exponentiate this to get T star prime is equal to some constant C1 e power minus psi square by 4 by exponentiating this. Okay. So, T star prime, the variable that I defined newly, was dt star by d psi. Okay. Is equal to C1 e power minus psi square by 4. Okay. Integrating this again, T star is equal to C1 integral 0 to psi d psi prime e power minus psi prime square by 4 plus C2. Okay. You cannot analytically integrate this further. Okay. Note that the variable itself appears in the limit of integration. When you integrate an equation, the variable itself, okay, appears as in the limit of integration. Within the integration sign, you have the integration variable. Okay. Within the integration sign, integration variable psi prime, okay, which is different from psi, which is in the limit of integration, okay, when you carry out an integration. Okay. This can be written in terms of what is called an error function. Okay. So, this term here can be written in terms of what is called an error function. Okay. Error function ERF of x is defined as 2 by root pi integral 0 to x dx prime e power minus x prime square. Okay. Here I have psi prime square by 4. So, I have to write x prime as psi prime by 2. Okay. So, this error function has certain properties. So, if I plot this integral 0 to x, okay, it increases linearly and then it saturates to plus 1. Okay. It goes to plus 1 as x goes to plus infinity. It will actually go to minus 1 as x goes to minus infinity. Okay. Okay. But for us, we only in the domain 0 to infinity. Okay. So, it goes to plus 1 and it has a non-zero slope at the center. That slope is basically 2 by root pi. Okay. This is the definition of the error function. Okay. So, therefore, in terms of this, note that I have x square here in the error function and I have psi prime square by 4. So, therefore, I have to make the substitution x is equal to psi prime by 2. Okay. And once I do that, what I will get is that T star is equal to C1 root pi, okay, error function of psi prime by 2. I am sorry, psi by 2, okay, because this is not the variable of integration, this is just psi itself, okay, plus C2. Okay. So, this is the solution for the temperature field that contains two constants. Those constants have to be determined from the boundary conditions at psi is equal to 0 and psi goes to infinity. Note that those boundary conditions were T star is equal to 0 as psi goes to infinity, T star is equal to 1 at psi equal to 0. Okay. At psi is equal to 0, this temperature is the error function itself is 0. Okay. At psi is equal to 0, the error function is equal to 0. Okay. Therefore, you require that if T star is equal to at psi equal to 0 implies that C 2 is equal to 1. Okay. And then the second condition, T star is equal to 0 as psi goes to infinity. Okay. This implies that C 1 root pi. Okay. Note that the error function goes to 1 as psi goes to infinity. So, C 1 root pi plus C 2 is equal to 0. Okay. And from this we get the condition that C 1 is equal to minus 1 by root pi. Okay. Substituting here C 1 is equal to 1 minus 1 by root pi, C 2 is equal to 1, okay, because this C 2 is equal to 1. The final expression for the temperature field becomes T star is equal to 1 minus error function of psi by 2. Okay. Okay. So, this is the equation for the temperature field. Okay. T star is equal to 1 minus error function of psi by 2, the scale temperature field. Now, we have to get also the heat flux at the surface, and I will write the heat flux q z in the z direction is equal to minus k partial T by partial z. Okay. Note that we had defined T star is equal to T minus T infinity by T naught minus T infinity, which implies that T is equal to T infinity plus T naught minus T infinity into T star. Okay. So, this becomes minus k into T naught minus T infinity, and we are also defined that psi is equal to z by root alpha t. Okay. Therefore, I have a factor of root alpha t partial T star by partial psi. Okay. So, this is the expression for the heat flux. Heat flux at the surface. Which is q z at z is equal to 0 is equal to minus k into T naught minus T infinity by root alpha t d T star by d psi at psi equals 0. Note that T star prime was T star by d psi. Okay. T star prime was equal to d T star by d psi, okay, which is equal to C 1 times e power minus psi square by 4. Okay. So, at psi is equal to 0 is just equal to C 1. Okay. At psi is equal to 0, this T star prime is just equal to C 1, which was 1 over root pi, okay, as shown here. Okay. C 1 was equal to 1 over root pi. Okay. Okay. So, using this expression, okay, T star by d psi at psi is equal to 0 is equal to C 1, and C 1 is equal to minus 1 over root pi. The heat flux at the surface becomes k into T naught minus T infinity by root of pi alpha t. Okay. So, this is the equation for the heat flux at the surface, and you can see as time progresses the heat flux decreases as 1 over square root of t. So, I will discuss a little bit more about this problem in the next lecture, and then I will apply it to another problem, which is a mass transfer problem, diffusion into an infinite medium, okay, and we will get a correlation for the Nusselt number or the Sherwood number for that case. I will continue this in the next lecture. Okay, I will see you then.